Okay, maximum and minimum values. In this section, you'll actually find that much of what we do is very much similar to what you did in Calculus 1 when you looked for maximum and minimum values before. But obviously, with the fact that we're dealing with three-dimensional shapes, surfaces, it does kick up the complexity a bit. So just keep in mind that there are some different elements, but be on the lookout for the similarities between this section and your Calculus 1 experience. So let's begin. Now, again, as I mentioned already before, we have studied methods for finding extrema of a function of a single variable. Now, you will use these methods to find functions of two variables. We'll start by considering a continuous function of two variables defined on a closed bounded region. Whenever I say closed bounded region, that usually means what I've said before in class, where you have like a beach canopy and it's casting a shadow onto the ground. That's what region R is. It's a closed bounded region, the shadow. And a lot of this is just a bunch of math jargon, but this is the shadow. And keep in mind that we do have the minimum and maximum values that actually occur on this region. And recall back in Calculus 1 days, we have the extreme value theorem, which deals with a region in a plane that is both closed and bounded. Now, I just want to kind of point out, too, that you'll see you have a lot of verbiage here. So I'm going to be going pretty quickly through these slides that look like this. So you probably won't have enough time to write all the words out. So once again, as I've mentioned before, later on I'm going to provide you the link to this video, and you're able to watch this in your own speed. You can slow down, fast forward, rewind, things like that. But during these lessons, for time's sake, I'm going to be flying through these types of slides fairly quickly. Yeah, so notice that we have a surface here. The maximum here is this point right here up top. And notice that if I just kind of project that point down to the shadow, it is actually well within the closed bounded region. Now later on, we will be dealing with also not only the maximums and minimums, but also we'll look at the extrema that are also on the border of the region as well. But we'll deal with that more later in the lesson. Now again, a lot of these definitions are similar to Calculus 1. Keep in mind that a minimum is also called an absolute minimum. A maximum is also called an absolute maximum. Recall, there is a huge difference between absolute and local. The best way I used to teach it in Calculus 1 is that a local extrema has a neighborhood around it, and an absolute extrema could have a neighborhood around it, but sometimes could actually occur on the border of the region. But just recall, guys, that the definition of a local extrema is in a region containing this interval here. Notice that the interval is not enclosed. It's from A to B. It's a local minimum, obviously, if all surrounding areas is bigger than the function itself at that point. It's a local maximum if everywhere around this point is lower than the neighborhood is lower than the actual point itself on any open disk. And again, remember, notice it's an open disk. All that means is that around the point AB, it's open, okay? Which means there is a complete neighborhood that surrounds it. Whereas an absolute, again, can mean either similar to a local or on the border of the region. Again, much like Calculus 1, we have things called critical points. And critical points in this section are found in a very similar way. to critical points you found in Calculus 1. In Calc 1, you found critical points by taking a derivative and then setting it equal to 0. I'm sure many of you know this. But because this is a function of two variables now, we must do a little bit more than just take the derivative once and set it equal to 0. And the way we do that is by using partial derivatives. And notice that not only are we taking the partial derivative with respect to x, we're also taking the partial derivative with respect to y. And the first step that we're going to do, this is very important. The very first step we'll be doing in these problems is you're going to be taking the partial derivative with respect to x, setting it equal to 0, doing the same thing for the partial derivative with respect to y, and you're going to solve for these two equations simultaneously. Also, we need to look for places where the derivatives do not exist. Again, Calculus 1, you did the same thing. And usually where the derivative does not exist is usually like at a corner or a cusp is typically where you'll find those. But it is similar to Calculus 1, with the only difference being that we're using partial derivatives now. Theorem 2 does state that if f has a local maximum or minimum at the point AB, then AB is a critical point of f. Keep in mind, not all critical points give rise to maxima or minima. Think about the function from calculus, the function y equals x cubed. If you look at the function y equals x cubed, it definitely has a minimum, it definitely has a critical point at the origin, but you'll notice that the graph of y equals x cubed has no min or max, but yet has a critical point. So please keep that in mind, guys. Just like in Calculus 1, just because you have a critical point does not mean you'll find a max or a min, as you'll see very shortly. So to clarify, at a critical point, a function can either have a local maximum or a local minimum or neither. Now, also in Calc 1, not only did you have a first derivative test, you also had what was known as the second derivative test. Now, in Calculus 3, we really can't use the first derivative test. The first derivative test does not give enough information to let us know if we have a max or a min. In Calculus 3, we almost have to apply the idea of a second derivative test. Now, this second derivative test is more complicated than your Calculus 1 days because, again, we are dealing with a three-dimensional surface. So, there are some similarities, but it does ratchet it up a notch to be three-dimensional. So be ready. But it is analogous. It does have some similarities. Now, again, the first step we'll be doing in order to solve or to take care of the second derivative test is we must start by taking the partial derivative with respect to x, the partial derivative with respect to y, setting them both equal to 0. Sorry, this one's the format's a little off. Set them both equal to 0 and solve for them simultaneously. This is going to help us figure out what is our critical point AB. And then we need to test the relative local extrema of f using this formula right here. Now, this formula right now might not make any sense to you. You might not want, where did this formula come from? You might be wondering. And, well, it's basically going to help you with the second derivative test. And essentially, it's going to measure, this value is going to help measure whether or not you have on your hands a minimum or a maximum. It's kind of like in Calc 1, when the second derivative measured the concavity of the function. This is kind of the same thing. But this is definitely a formula you're going to want to memorize. Notice it's the the second derivative with respect to x multiplied by the second derivative with respect to y minus the square of the partial derivative with respect to x then y. All three of these are evaluated at the critical point AB. Now, once you have this thing calculated, and this will give you a positive or negative number. If it's positive, and on top of that, the second partial with respect to x is also positive, then you have yourself a local minimum. If you literally follow this, you'll have a local minimum, guaranteed. Now, case 2 is similar. Again, if d is greater than 0, but this time the second derivative with respect to x is negative, then you'll have on your hands a local max. Now, what if, though, d is negative? What if d is less than 0? Well, if d is less than 0, it's very quick. You can actually go ahead and say it's called what's known as a saddle point. Now, you might be wondering what's a saddle point? Well, again, it's kind of like dealing with the graph y equals x cubed. Y equals x cubed has no minimum or maximum at the origin, but it definitely still has a critical point there. And that's kind of the same thing here, is that a saddle point is essentially, I'll explain that at the bottom here, is essentially a critical point that is neither a local min or max. And then for the step 4 here, the test will be inconclusive if d equals 0. You don't have to worry about that in this class. I do not provide examples like that. But if you ever do have a situation where d equals 0, then that is going to be a little bit of a tough problem to be in, but there are other ways around it. But lucky for you guys, I do not go into depth with that. Pretty much every problem that you encounter in this class is going to involve one of the first 3 cases. So let's get into an example here. I'm going to go ahead and just kind of discuss this this map here. Now, this map is a map of level curves. And remember, what are level curves? Level curves are curves that you raise up or depress downward. So that way you can kind of visualize what this surface could potentially look at by simply looking at the values of their z values on these curves themselves. So for example, notice here that I start here on this level curve here. It's negative 2.5, but then all of a sudden the numbers start going down, down, down as we get closer to this little oval here. We can pretty much assume that it's symmetrical. Look over here though. You'll notice that as we get away from this little epicenter, the numbers also go down as well. Okay. Now this is going down, but this is going down also. But notice that these numbers are going down toward the epicenter. These numbers are going down away from the epicenter. So that's going to be 2 different situations. But basically, let's just quickly discuss what we think is happening in this picture. Now, go ahead and take a look at these numbers. I have -1, -1, +1, +1. So that means this epicenter over here is the point -1, 1. And this epicenter down here is the point -1, -1. And this epicenter over here is the point 1, 1, 0. Now, as we're moving toward this epicenter here, -1, 1, as we're moving toward it, it seems to be going down in elevation. The numbers are going down as we get towards the epicenter. So to me, that would indicate that this would be a local minimum, because as I'm getting closer to the epicenter, the numbers are getting lower. Okay, so to me, that this will be a local minimum, and I think it's safe to say that this is probably symmetrical also. Now this could potentially be a local max, but because they did not give us enough information, I'm going to go ahead and assume that these are symmetrical. Whoops. Sorry about that. and that this will also be a local minimum here at the point -1, -1. Now this point here, as the numbers are getting closer to the epicenter, the value is getting higher. So the elevation of my z values are growing as I get closer to the epicenter here. That's because this is probably a local max. Now the only way really to know whether or not these are local mins or local maxes is to check it mathematically, and we'll do that in a moment. Now, if everyone turns their other attention to where these level curves are kind of crossing each other, these typically will be saddle points. So notice that I have a saddle point here at the point 1, 1. If I go right 1, up 1, I have a little place where it crosses. That, to me, typically is indicating a saddle point. And you can basically tell it's a saddle point because if you go off in this direction, well, let's go downward. If you go off in this direction, the numbers are getting bigger, correct? But if you go off in this direction to the left, the numbers are getting smaller. So it's going bigger this way, but smaller this way. There's no like uniform level curve behavior. So when one way is going bigger, the other way is going smaller, you can pretty much guarantee yourself it's a saddle point. And same thing here. As I move to the right, the numbers are getting bigger. As I move up, the numbers are getting smaller. So the same thing here, guys. This is probably going to be a saddle point as well. So I want to confirm our discussion, or at least my my take on what was just discussed here. So again, just as a summary. This I believe to be a local minimum, and its symmetrical counterpart down below is also a minimum. And then also this point over here is going to be a local maximum with the point 1, 1, 1, -1, and the point -1, 0 being saddle points. So we're going to confirm our thoughts on this by solving for the partial with respect to x and the partial with respect to y, both equal to 0 simultaneously. Now, before I even begin, this is a really important part I want to point out. So please hear me when I say this. Before I even begin, what we're about to do is very repetitive. So that's good news for a lot of students because we're going to be doing something over and over and over again and getting really good at it. So what I'm about to show you guys is going to be happening over and over and over again. The process will be the same pretty much for every single example we do for the rest of this section. However, the little details within the process change from problem to problem. So for example, solving for these partial derivatives simultaneously will not always be solved simultaneously in the same way. You'll have to use your algebra skills, your ability for inspection, your intuition to see what's the best way to solve for this little system of equations for every problem, because each problem is going to be different and each problem is going to present its own little set of issues that you got to work around. But the good news, at least, is that you will always start problems the same way. We're going to solve for these partials simultaneously, and let's go ahead and do that here. So notice up top, I have my function here. It's 3x minus x cubed minus 2y squared plus y to the fourth. And I want to solve these simultaneously. Well, first, let's go and take the partial with respect to x. Obviously, it's going to be 3 minus 3x squared. These two latter terms get canceled out. I set that equal to 0. And if I set that equal to 0, that implies that if the partial with respect to x is equal to this, then that implies that we will potentially have critical points when x is positive 1 and negative 1, which, if we go back to the picture here, you know, that's obvious to see. And then let's go ahead and do the same for the partial with respect to y. Notice that if I take the partial with respect to y, set it equal to 0, I get this little equation here, which is very easy to solve, which means either y is 0 or this difference of squares is 0, which gives us the possible numbers of y equals 0 or plus or minus 1. So there's a lot of numbers here. I got plus or minus 1 for the x. I got 0 plus or minus 1 for the y. And this is, again, where it gets more complex, where we have to be patient. And that is, whatever values of x and y you discover, and this is very important, you must consider all possibilities and all values using these numbers that we found. So, so having said that, we go ahead and hopefully this kind of makes sense. We found the values of x, we found our values of y. So that means all of our possible critical points are the following. My possible critical points here are 1, 0, negative 1, 0, 1, 1, negative 1, 1, 1, negative 1, and negative 1, negative 1. And if you go back to the picture, and you should have this in your student notes. If you're not the type of student that prints out the student notes, you can at least pull it up on your phone, and you can still see the picture at all times. And you'll see that there's something interesting happening at every single one of these points from the previous slide. So far, this is confirming my some of my initial thoughts. But these don't tell me whether or not they are minimums or maximums or saddle points. For that, I have to actually go ahead and test them out. Now, if you recall, let's go back here real quick. If you recall, there's a process here. We need to first evaluate this letter D, which involves the second derivatives, xx, yy, and xy. And we need this formula to help us understand whether or not we have ourselves a local min or a local max. So let's go ahead and check. Now let's first find these second partials. We should be very, very good at finding second partials by now. Here's my second partials. So again, hopefully you already have the function written down. If you don't, please feel free to rewind and get that function written down. But here's my second partial with respect to x, my second partial with respect to x and y, and my second partial with respect to y. Now, using these formulas, I'm going to go ahead and plug it into what is D. And let's go ahead and evaluate first at the point 1, 0. So we take the formula here, which is the second partial evaluated at 1, 0, times the second partial of y evaluated at 1, 0. I'm going to subtract the second partial xy evaluated at 1, 0 squared. Now, this middle second derivative is already 0 without even me plugging in any numbers at all. So this part's going to be canceled out very quickly. And in this particular case, I end up getting negative 6 times negative 4, right? Because if I plug in a 1 here, I get negative 6. If I plug in a 0 here, I just get negative 4. Multiply those out, minus the 0, we get 24. Well, that gave me a positive result, yes? Well, also keep in mind that, if I go back, here, well, I got a positive result for my letter D here, my D value. Well, that's going to help me with either case 1 or case 2. So I have a positive D value. So that means it's definitely going to be either a local minimum or a local maximum. Now my job will be to find out whether the second derivative with respect to x is positive or negative, and that will actually determine whether or not I have a minimum or a maximum value. Well, as you can see, if I go ahead and take my 0.10 and plug it into f double x, then I do actually get a negative 6, which is less than 0. So once again, I get a value of D that's positive and a second derivative with respect to x that is negative. So going back to our little rule book here, we have a positive letter D and a negative second derivative. So that's going to be case 2. So that means we have ourselves a local maximum. So since D is positive and f double x is negative, then 1, 0 is what's known as a local maximum. And just so you know, this is the same process we'll be doing for all 6 of those points. Now, many times when you're given a lot of points like this that you have to test and check, many times a lot of the points have the same behaviors. And so if you're very good at algebra and you can kind of see what's going on, you can probably eliminate some of the work. But yes, unfortunately, we have to check every single point to determine which critical point is minimum, which critical point is maximum, and which one is a saddle point. But again, the good news is that it's a very simple process. You simply just plug it into the formula and let it do its thing. So let's take a look at 1,1. So again, the same thing is we want to find the value of d and the second derivative with respect to x. Now, if you were to plug in 1,1 into the formula from the previous page, here it is, right here. If you were to plug in 1,1 to where you see AB, well, according to this particular problem, we end up getting negative 48 out of it, which is a negative number. So because we get negative out of it, it's nice because according to my rules, whenever d is negative, then it's immediately a saddle point, and we can move on. And a really quick side note, you'll notice, and please do these calculations yourself to verify. I'm just basically showing you guys the pathway, but it would be a good idea for you to verify these things yourself. And by the way, 1 and negative 1, 1, negative 1, negative 1, 0 are also saddle points. And if we go back to the picture that you already should have in front of you, you'll notice that again those confirm those little cross sections here we have, where the level curves are crossing each other. That confirms that prediction. Finally, for the last 2 points, we do get a positive d value for negative 1, 1 and negative 1, negative 1. And then again, evaluating these same points, plugging them into the second partial with respect to x, those also become positive values, which means that will give us a local minimum. And before I move on, because like I said, we're going to be repeating this process over and over again of the second derivatives test. I know there's a lot of verbiage here, but everything on here is going to be repeated over and over and over again for the remainder of this section for the most part. There's a few things that might change a little bit, but pretty much this is kind of the idea of what we're following. Later on, when we get to finding absolute maximums and minimums, we won't really need to use this formula so much because this only can tell me if it's a local minimum or maximum, not an absolute. I'll get to that later. But if you could really kind of digest this slide and just read it over and over again and just do like 1 or 2 problems, you'll find that this slide here is very useful, and it's very methodical, and it doesn't really change hardly ever, with the exception of some like small little twists, but overall it's basically the same idea. So why don't we do an example, like just a straight up example where we're not given level curves, we're not given a picture, we're just given the function itself. And again, it's going to follow the same exact process. So my question to you is, what is our first step? Our first step is to, once again, find the first partial derivatives of both x and y, set them equal to 0, and solve simultaneously. You'll notice that that happens over and over again. So let's get to it. All right, so let's go ahead and take the partial with respect to x here. We get 4x plus 2y plus 2 equals 0. Here we get f sub y equals 2y plus 2x plus 2 equals 0. I hope you agree based off of this function here. They're kind of similar to each other, but they have a slight difference with the x terms. And we're going to go ahead and solve for them simultaneously. Now I'm going to solve for this one a different way. Now remember, we start off the same way, but each problem presents its own little twists and turns. You'll notice in the last problem, I went ahead and just solved for x straight up. And then after that, solved for y straight up. Here, I can't quite do that. Here, what you're going to want to do is one of 2 things. Either solve for y or x here and then plug it into this over here, or since they're both equal to 0, you can go ahead and just set them equal to each other. That's It's kind of like a cheap way to do it. And just go ahead and set these two equal to each other. And this is just going to be another way to solve for this. So this problem is definitely going to be different because instead of ending up with actual numbers, the last example gave me actual numbers. It gave us plus or minus 1 or 0, then plus or minus 1. Here, though, when we solve for it, we do get x equals 0, but sometimes we'll get algebraic expressions, so be on the lookout for that, but I'll explain our ways around that momentarily. So here we get x equals 0, and what you want to do is take that x equals 0 and go ahead and sub it into either f sub x or f sub y. Either way, it's going to give you y equals -1. So we actually do come up with the actual number. And then take that y equals -1 and again plug it into either one of these to find your x value, which is in this case is going to be 0. So once again, we solve for x equals 0, we get y equals -1. So that gives us the point 0, -1. Now, notice how in the last example we had 6 critical points. Quite a bit, right? Here we only have 1, so it's going to be a lot less work. But it's not always that way. Obviously, sometimes you have 6, sometimes you have 1, sometimes you have 20, sometimes you have 0. Now, on top of having our critical point, we still need to have our double derivative values. Now, in this particular case, this problem is a little bit different because once I take the second derivative of x or y or xy, notice this time we actually just get straight up numbers. I didn't even have to plug in the 0, -1. It just happened to give me numbers right away. And that happens sometimes. And then once again, we use that formula. Go ahead and plug these values. Again, what is it? It's 4 times this 2 over here is 8, minus this middle term squared, which is 4. So 8 minus 4 gives me 4, which is positive, right? And as we already can see from the double derivative with respect to x is already also a positive. So in this case, I have a positive, right? So again, if I go back to that methodical slide, that's case 1. When you have a positive, you get a local minimum. So the question here was twofold. I'll go ahead and pull the question up again. Okay. The question's asking us not only find the local maximum and minimum, but be sure to find out where it is actually located. But they actually want the value of this. So the local minimum here is located at 0, -1, but the value is actually -1. So actually, guys, right over here would be the answer here. In fact, let me get a, whoops. The answer to this particular problem is going to be this, this -1 value right here. And as I mentioned before, and I'll mention it again, this concept has many similarities to finding max or min values in Calculus 1. Again, how do we find maximum, minimum values? We take derivatives, and then after you take derivatives and find critical points, you take those critical points and actually physically plug them back into the original function to get an actual value. And that's what I did here. The answer to this question is -1. So I have a picture for you guys that shows you what it looks like. This is what the surface looks like. And as you can see at the ground floor here, at the point 0, -1, we do actually get a local minimum there. So that's pretty easy to see. Let's try another one. Same exact approach. Same exact approach. So again, I think a lot of students are going to like how methodical this section is and how you can find minimum and maximum values the same way every time. But once we take the first derivative with respect to x and y, keep in mind that you will not solve all of these the same. Now, me personally, as I set both of these equal to 0, I think it's going to be nicer to solve for the partial with respect to y first, set that equal to 0 and solve for that first. The reason why I say that is as you do it, you basically get kind of a nice explicit expression here. So again, set the partial with respect to y equal to 0. You get this here. Yes? Go ahead and reveal those again. You get this here. Solve for y, we get this nice negative 1/2 x squared, like parabola here. And the reason why that's so nice is because now I can take that and substitute it back into the f of x function here, and then at that point solve for 0 itself. Now, once I take this and plug it into the partial derivative with respect to x, I'm obviously going to replace this y here with negative 1/2 x squared, which is going to cause my equation to end up becoming like this. So notice how I took one of the equations, in particular f sub y, and solved for it itself, and I used that to help me simplify the second equation. So sometimes you can solve for equations straight up like I did in the first example. Sometimes it takes a little more work. In this case, I had to kind of toggle back and forth between these two different equations to get what I wanted. And again, use your intuition, use your algebra skills, and experiment. Don't be shy to do kind of strange and wondrous things to make sure that you get to the result you need. Because notice here, once I got to here, I now have a very easy algebraic equation, which, solving for this, you end up getting either x is 0 or x is plus or minus radical 2. But then, of course, you're going to sub this back into f sub y, because we don't want just x values, we also want the y values. And I want to take the time right here to point out a couple things. Notice how so far you've probably seen this a lot. You've seen me use the word sub a lot. And that's really what this is. This is, we're subbing a whole lot of values back into previous values. So again, it's a lot of algebra happening here. So keep that in mind as we continue. And remember too that whatever previous relationships you've established, like for example up here, this relationship between these two guys, is always valid, and you can always use it to your advantage when needed. So because I have the point of the numbers 0, plus or minus radical 2, and then I plug it back into the other partial derivative with respect to y, my critical points are going to be 0, 0, rad 2, negative 1, and negative rad 2, negative 1. And by the way, you can plug these back into the original f sub y equals 0, or you could actually also just take these guys right here and plug them back into here. So that's also okay as well. Now this isn't so bad. The first problem we had 6 critical points. The last one only had 1. So this one has 3, so it's not so bad. But again, you're just gonna follow the same process that you did previously. You're gonna use that formula that involves the letter D there. Now, I'm assuming everyone in the class now knows how to calculate your double partial derivatives, and then you go ahead and plug it into that formula D. Once again, it's the same one here. This guy right here. Okay. Please plug it in there to discover where it's negative and positive. Now, at plus or minus rad 2 minus 1, it's negative. So that means at both of these points here, plus or minus rad 2, negative 1, they're both saddle points. Whereas at the origin, we actually get a positive number, and then we go ahead and proceed to calculate the double derivative at the origin. We get a positive number. So this, again, is the first case. When D is positive and the double derivative with respect to x is also positive, we have ourselves a local a local minimum. So I don't know what happened there, but okay. So yeah, so it's very methodical. Again, notice that I'm doing a lot of the same things. We're solving for the first partial derivative simultaneously equal to 0. Then we're calculating our double derivatives, plugging it into the formula for D, and seeing which case it is. 1, 2, or 3, and in rare, if not no cases, this semester is 0. Now, I do actually have one more of these, and that's this guy right here. Okay, but I'm actually not going to do it for you. I am so confident that you guys can do this yourself that I'm going to go ahead and just give you the answer to this problem right here. This is, please go ahead and try to do this yourself. Do this right now. If you're watching this video on YouTube, please pause this and go ahead and try this right now. Not only do you only get one critical point, the critical point will prove itself to be a local max, which means that D is positive and the partial with respect to x twice is going to be negative. It's going to be the second case. So I would recommend that you pause the video now and try this yourself. It's the same exact methodical steps, and I highly recommend you do it right now. That's what this one looks like. All right, so now we're going to take a different turn and talk about absolute maximum, absolute minimums. Now, there are some similarities to finding local maximums and minimums, but there's an extra twist to it. But the nice thing about finding absolute maximums and absolute minimums is that there's actually, in some ways, less work, but however, in other ways, there's more work. So it's about the same amount of work. So if you found the last 3 or 4 examples to be quite simple and methodical, you'll notice that the following 3 or 4 examples are very similar. They're very methodical, they're very simple, and they repeat themselves quite a bit. So let's get to it. Now recall back in Calculus 1 the extreme value theorem. An extreme value theorem not only checks the extreme values within the interval, but also on the endpoints. If you recall, back in Calculus 1, whenever you were asked to find an extreme value, not only did you have to take the derivative and find any critical points within the interval, but you also had to check the endpoints. Now, in Calculus 1, it was very simple, though, because those were just functions of one variable, and all you had to worry about was where you had a peak and where you had a valley. Well, in Calculus 3, not only do we need to check the endpoints, we actually need to check entire borderlines, Because remember, we're talking about a beach canopy flapping in the wind, and it casts a shadow onto the ground. And that shadow, if you stay within the shadow, is like a typical critical point, like we found in the last three examples. But then you also have the borders of the shadow. You got to check those borders as well. So we will be checking those borders on what's known as the closed interval method. And this only can occur in a closed set that contains all its boundary points. And we must include every single point on that boundary curve for this to work. All right, so just some examples. So we will only be dealing with closed sets in this section. No sets like this where it's either completely open, even just one point open, or partially closed, partially open. So we're only dealing with completely closed sets. Now again, this is a very methodical process. Once we do one or two of these, you should be able to do all of them. Now again, each problem comes with its own little twists and turns, but the methodical process will be the same every time. So how do we find the absolute maximum or minimum values? We first start by finding all values of f at the critical points of f in D. Now this is nice because this is actually just like what we found earlier. In the last three examples, how did we go about finding the critical points? Well, we went ahead and solved for the first derivative simultaneously equal to 0. Well, here we're going to do the same thing. We're going to actually start off the same exact way. But the nice thing about this is because we're looking for absolute maximums and minimums, we actually do not need that formula for D from the previous slides most times. Then after that, just simply find the extreme values of f on the boundaries. And the largest of these from steps 1 and 2 will be the maximum, the absolute maximum, and the smallest will be the absolute minimum. And it's literally going ahead and finding the same process. It's very similar to the last three examples. Again, as I want to really emphasize, step 1 is just like finding the critical points from the last three examples we just did. So having said that, let's go ahead and take a look at this one. I'll give you a moment to go ahead and write down this example onto your student notes. We're going to look for the absolute maximum and minimum values on this of this function on the closed region, in this case a closed triangular region. Now again, remember guys, D is the closed triangular region, okay? And basically guys, D is the shadow that the beach canopy casts down to the ground. It's not the beach canopy itself. The beach canopy is this function here. F of xy is the beach canopy. D is the shadow that it casts onto the ground. So again, I mean, I know I'm a broken record. I'm actually repeating myself quite a bit, but it bears worth repeating. It's worth repeating here that for this particular problem, guys, these examples start the same exact way as the last three examples. But be sure that your critical points fall within the given region. That's important. Now, just so you know, it would be a good idea to sketch these regions before you start, but because you can start these examples similar to the previous three we just did, you actually do not need to draw the picture to find those critical points of the function itself. You just simply do the same thing we did before. We're going to go ahead and solve for the first derivative with respect to x and with respect to y. Set them both equal to 0. Solve them simultaneously. Let's start there. So I'll just kind of cover up the region for a second. Now, in this particular case, guys, we only get the critical point 0, 0. Looks like we only get 1 here in this case, which is nice. But that's not all. Remember, just like in Calculus 1, whenever you found the critical point in a closed interval, not only do you have to plug in this value into the original function, but you also have to plug in any points along on the endpoints. You have to check the endpoints to also see if you have an absolute maximum or minimum. So the easy part's done. Now, and again, I hope you guys have this written down. The next part is we need to go ahead and check the region itself. So here I'm going to go ahead and actually draw the picture for you guys. And I know there's a lot of verbiage up here, so I'll just go through this as best I can. In fact, let me kind of cover up some of, no, it's not going to let me. I'm going to go ahead and cover up some of this stuff here. Let's see. So I'm going to cover up this stuff over here. You might have already seen it, but so here's our region. It's our triangular region. Notice that I went ahead and named each side. I labeled each side. So this is line 1. This is line 2. This is line 3. I didn't have to call it these things. I could have called line 1 this guy, line 2 this guy. It doesn't matter. But the point is that we need to evaluate what's going on the borders themselves using the function they gave us. Let's go and start with the easy one. On the first border, L1. So I think we all can agree that L1 is a horizontal line, and horizontal lines are always y equals some constant. In this case, I think all of us can agree that this line is the equation y equals 1. Well, as I said before, we will be substituting these values into previous relationships. In this case, we're going to go ahead and substitute y equals 1 into the original function given to us, this guy right here. So wherever I see a y, I'm going to replace it with the number 1. So everywhere you see y, replace it with a 1. So f of x1, x squared plus 2x times 1 plus 3 times 1 squared. Once you plug that in, you end up with x squared plus 2x plus 3. And the beauty part about this is that once you have your simplified version of the function, this now becomes exactly like Calculus 1. Notice that I have an interval. I have everything you guys need from Calculus 1. We're going from -1 over to 2 on this function here. So we're going to find max and mins using Calculus 1. How did we do that before? Well, we took a derivative, right? We take the derivative of this function here. I think we all agree that we get 2x plus 2. We set that equal to 0. And then we end up getting x equals -1 for our first critical point. Now this is a critical point only along the border. That's okay. And again, notice that x is going from -1 to +2. So what we do is we take x equals -1 and we actually plug it in here. Yeah, let's go up here. And not only are you supposed to plug in oops, sorry about that. Not only are you supposed to plug in this value into here, okay? But you're also supposed to plug in the endpoints also into this function as well. So we're going to plug in x equals 2. We're going to plug in x equals -1. And sometimes you'll get points in the middle. You'll see in a moment. Sometimes you get points somewhere along this border. It just so happened that our critical points happen to be one of the endpoints. Now we plug it in. We end up getting a max at x equals 2 with f of 2 equal to 11, and a min at x equals -2 of f of -2 equals 2. Now that's just the first border. That's just L1. So let's go ahead and move on to L2. That's this guy right here. So L2, as I think we all can see, that L2, x is the same throughout the entire thing. This is a vertical line. So on L2, we actually have let's pull this up here. The vertical line x equals -1. And for that, we go ahead and take that and plug it into the original function given to us, where everywhere you see an x, you replace it with -1. And we simplify, we end up with this. And once again, just like calculus 2, you take the derivative, and then you find out its critical points. Now this one's actually kind of interesting. Notice that this time we got y equals 1/3. Well, let's go and take a look at the picture. If we take a look at the picture here, y equals 1/3 is like a point like right here. It's like right here on the border. I think we all agree, yes? So it's in between the two endpoints. So in the last example here with L1, our critical point happened to be the endpoint up here. But on this case, our critical point is like somewhere around here, where y is 1/3. So not only are we going to have to test this number, y equals 1/3, we're also going to have to test where y is -2 and y is +1. So again, notice again in L2, we're going from -2 down here up to +1. And from -2 to +1, L2 has a max at -2, because if you plug in -2, you get 17. Whereas it has a min at 1/3, because if we plug in 1/3, we get 2/3. Now, okay, before I continue, notice, all we're doing is we're finding these critical points and determining their values, right? So 11.2, sorry, this should actually have two variables, but it's fine. And then this one here, we have a value at -1, -2, and we have a value here at -1, 1/3, correct? So far I have 4 values to compare. But now I need to check now my values along this line, L3. Now this is not just a vertical or horizontal line, it's diagonal. So because it's diagonal, I have to find the relationship here. Now in this particular case, let me go ahead and cover up some information just for now. I think we all can agree that L3 is actually the line y equals x minus 1. So if I go back up again, it does cross the y-axis at -1, and it looks like to have a slope of +1. So I hope for everyone in the class you guys can all see how this line is y equals x minus 1. Keep in mind, we're coming from x is negative 1 all the way to x is 2. So again, we substitute. Wherever we see a y, we're going to substitute it with x minus 1 into the original function. Just literally plug it in. Here we go. Everywhere I see a y, I replace it with x minus 1. So you'll have x squared plus 2x times x minus 1 plus 3 times x minus 1 quantity squared. And of course, you're going to want to simplify this a bit. There you go. So that's the shape of that curve on that line. Once again, we utilize our calculus 2 skills. Take the derivative, set it equal to 0. In this case, we solve for x, we get 2/3. So if I were to scroll back up, that means I have a critical point. Looks like to be somewhere around in this area, I would say. So we'll have to check this area and its endpoints. So we get 2/3, and then we go ahead and plug in our values. Now notice I'm actually kind of repeating myself here. Notice that L3 and L2 share a similar endpoint. They both share the endpoint -1, -2. So it's no surprise that they have the same value of 17 there. And it has a minimum. At this point, plug in 2/3, we get 1/3. And our final step to doing this problem is now we got to compare all these different values. So, for example, we have these values here, right? 1, 2. We have these values here, 1, 2. Well, I guess it's just 1 because we're repeating this one. And then we have these two values here. So we have 5 values to compare to. And essentially, the largest of these values will give me my max. The smallest of these values would give me my min. So obviously, the largest of these values is 17. So that's going to be my max. The smallest of these values seems to be, well, you got a 2 there. But then we have a 2/3 here. That's smaller. But then even smaller than that is a value of 1/3. Now, we can go ahead and say that this 1/3 could possibly be my absolute min, and the 17 here could be my absolute max. But let's not forget, if we scroll back up to the very beginning of this problem, we also had this point 0, 0. This point 0, 0 is well within the region here. It's right here at the origin, in the middle. I think we all can see that. And because it's well within this region, this is also a point that we have to consider. This point we must plug in to the original function, which is this function right here. And if I plug in 0, 0, I obviously get 0 out of it. And clearly, 0 is smaller than 1/3. So my final answer to this problem is actually going to be, my absolute minimum will be f of 0, 0, where 0, 0 is the critical point we found at the very beginning of this problem. And also my absolute max will be f of -1, 2, which has a value of 17. And as I mentioned, this is very methodical, so let's go ahead and do another example with a different region, but it's going to be the same exact approach. So here, we go ahead and start out the same exact way we've done all of these problems. You start by first taking the first derivative with respect to x, and then the first derivative with respect to y, setting them equal to 0. This one obviously is super easy. Just add 1 on this one, add 1 on this one. Gives us a critical point of 1, 1. We go ahead and take that critical point, we plug it into our original function here, and we end up with a value of 0. So let's go ahead and kind of keep this in the back of our mind, and we'll come back to this later, and potentially this could be one of our answers. It might not be one of our answers at all. We'll have to find out. We'll wait and see. Now let's go and take a look at the actual region. The region is bounded by the parabola y equals x squared and the line y equals 4. Pretty easy to graph that. As I graph that, it should look something like this. I think that comes as no surprise. So here's my region. Notice how our critical point just happened to be on the border itself. That was just purely coincidental. But let's go ahead and take a look. Now I'm going to go ahead and call this line up here line 1, and I'll call, even though this is not really a line, we'll just go ahead and call this line 2, that little curve at the bottom. You have to check the borders now. So at line 1, we all know that y equals 4. Pretty easy to see. So simply go ahead and take that 4, and we again we plug it into the function given to us right here. Wherever I see the letter y, I replace it with a 4. It's going to give us this, which reduces to this. Now, notice again that x is going from -2 to +2. So for x is -2 to +2, again, set this equal to 0. We end up getting 1. And then plug that 1 into here, and we end up getting, let's see, 5 minus 1, so it's back to 4. 4 minus 4 is also 0. But then, if you plug in the endpoints, as you can see I plugged in the endpoints, I get 3 and also -9. So that gives us some more values to consider. So now let's take a look at this curve down below. This curve down below gives me, let's make this a little smaller here. This curve down below gives me the relationship y equals x squared. So what we do with that y equals x squared is we take it and we plug it back in once again to the original problem, this guy right here. Wherever I see a y, I replace it with x squared. And then I go ahead and simplify it. I end up getting this here. Take the derivative, set it equal to 0. I end up getting these two values right here, -1/3 or 1. Now, I'm not going to really worry too much about 1. We already took care of that when I found the first critical point. But let's go ahead and take a look at the 1/3. We plug in the 1/3, we get -1/3, 1/9. Plug it in, we get 32 over 27, which is like, a little over 1. But pretty much we have all the different values that we need. So the values we're going to consider is this guy, which we already had, and these two guys right here. So actually, in this particular case, it looks like our max and min occurred at these two endpoint corners right here. Now, there's no way of knowing that the absolute maxes and mins occur on the endpoints, because they don't always occur on the midpoints. So we can never assume that. You still need to show all this work. So even though these happen to show up on the endpoints, I still need you guys to show all this work, proving that you found every single critical point, every single possibility where there could be a minimum or a maximum. It still needs to be shown in a quiz or a test. And for emphasis, just a final conclusive statement. Our absolute max is f of 2, 4, which equals 3. Our absolute min is f of negative 2, 4, which is negative 9. Okay, let's move on to some more examples. Now, the next two examples are application problems, and they're actually they're fairly difficult to navigate through. But I want to assure you, for this example and especially for the next example, the process is exactly the same. So if you've been liking the process so far, then you should really be okay with what we're doing here. It's the same exact process. Keep in mind, again, you're given a relationship here, and this relationship must be maintained. And particularly, they want us, in this particular case, they want us to find the shortest distance from this point to negative 2, 3 to this given point here. Now, again, this is all about maximization and minimization, basically optimization is kind of the idea. So let's go ahead and get right into this one. Now, when we're talking about the distance from a point to some other object, it's still going to be based off the distance formula. The distance formula being this guy here. I'll go ahead and make this a little bigger. This should be familiar to us. Hopefully, everyone in the class basically knows where this has come from. The distance between 2 points in 3 space. We've done it before in class. And basically, it's the distance between the plane, which is the x, y, z, and the point itself, which is 2, negative 2, 3, which is the point I have here. Now, there's a couple things I need. Not only do I need this formula for the distance formula, and I want to minimize this distance, but also I'm actually going to need something else. I'm going to need the relationship that z has with x and y. We don't want to have 3 variables. We want to have just maybe 2 at the most. So if I go ahead and take that z here and I solve for it, I end up getting z equals to 1/3 times the quantity 6x plus 4y minus 2. Okay. And what I'm going to do with this relationship here is I'm going to go ahead and actually take this relationship here, and I've said it before, I'll say it again many times. I take this relationship here, and we're going to sub it back into the distance formula. Okay. So take this relationship, plug it into the distance formula. For many of you, you might be thinking, well, this is making it look even harder. But trust me, this is the way to go. We're going from a function of 3 variables to a function of now 2 variables. So based on that alone, I'm sure every student can understand a function of 3 variables is much more complicated than a function of 2 variables. But of course, what I want to do is I want to simplify this z term to clean it up a little bit. But I want to tell you a little trick also. Now, hopefully you learned this from Calc 1. This square root here does kind of complicate things when we take derivatives. So what I propose you do instead is you go ahead and square both sides. And we end up getting this. Okay, so again, I clean up this over here. I distribute the 1/3. I subtract the 3, I end up with this over here. And then you square both sides because you're going to find that this d squared expression is going to be much more easy to differentiate than the square root expression here. But once I have this expression here, this problem becomes just like the other ones from the previous examples. Like this is, I could almost stop here and let everyone in the class do this themselves and feel justified because it's almost exactly like the other problems. In this case, I'm going to go ahead and let my f of x, y be the d squared. So once again, we solve it the same exact way. We're going to go ahead and take the partial with respect to x, the partial with respect to y, and then solve for these two equations by setting them both equal to 0 and solving them simultaneously once again. Now, I think everyone in the class could agree that if I take the derivative of this with respect to x, I get this first line here. I take the derivative with respect to y, I get this next little last line down here. Once again, you're going to set each one of these, set them both equal to 0, and now we have a nice system of equations. Now, this system of equations does reduce down to these two equations right here, which look a lot cleaner than this up here. Okay, but then you solve for the system of equations, you get kind of an ugly pair of numbers: 164 over 61 and negative 94 over 61. Well, if you take a look at the title of the example, it's asking for the shortest distance. Now, these are the values at which the shortest distance occurs, but you still need to take these two values here, okay, and plug them into the distance formula way up here, okay? So you plug them into here. It gets kind of annoying. Or you can actually plug it into the d squared expression, but make sure you take the square root after the fact. And we end up with the distance of 7 over radical 61. Is our answer. But again, notice it's very similar to the previous examples we did, just with its own little twists and turns. So I really want to emphasize that. I really want to emphasize how this section is very methodical. It's very consistent. And I want you guys to master this process because it's done the same way time and time again. Now, with this last example of this lesson, it gets really funky here. So you're going to have to be patient because not only do we not have numbers, it's going to be using variables, but you're going to have to use a lot of abstract thought here. So here, again, instead of minimizing distance, here we're trying to maximize the volume of a rectangular box inside a sphere of radius r. So what I want to point out is a couple things. One, here's my box, and then the box here, it's kind of hard to see, but every single one of these corners of this box, so this corner here, this corner here, this corner here, all these corners are all touching the sphere. Now you might be thinking, well, how in the world is this corner touching the sphere? Well, it's touching this side of the sphere. So it doesn't look like it's touching the sphere, but it actually is. And we want to maximize the volume of this rectangular box. So let's do that. For simplicity, we're going to center the sphere at the origin, 0, 0, 0, which will give us the equation of the sphere of x squared plus y squared plus z squared equals r squared. Also, for simplicity, it's going to be wise for us to orient the box so that its edges are parallel to the x, y, and z axes. So what I'm also going to do here is I'm going to go ahead and take a bird's eye view of what we're looking at here. So once again, here's the picture in 3D form. If I go up here to the top and look down on this box and sphere, I'm going to essentially see this cross section right here. Okay. So I'm above the sphere, looking down. And again, once again, it doesn't seem like it, but the box is physically touching the sphere. So like every corner, see this corner, X, Y, Z corner here? It is actually touching the sphere, but it's touching this side, the top side, or the upper hemisphere of the sphere. And because of this, I think we can actually see that the dimensions of this box, since I centered the sphere at the origin, and I created the box in such a way where the edges were parallel to the x and y axes and also the z axis, I think we all can see that the length of the box is 2x lengthwise. The width of the box is 2y, and I guess those are interchangeable. It doesn't really matter what's length or width. But definitely the height of the box will be 2z, and that's actually coming up at us. We can't really see it here, but it's coming up at us. And each one of these, the 2x, 2y, and 2z, are all found the same way. And let's keep in mind, again, let's remind ourselves that the question's asking us to find the maximum volume of a box. And thinking back to our basic geometry classes, the volume of a box is going to be length times width times height. I think most of us know this. And in this case, if the length is 2x, the width is 2y, and the height is 2z, then the volume of this box is going to be 2x times 2y times 2z. Now, like previous examples, I do not want 3 variables. I want 2 variables at most. So to do that, once again, I'm gonna try to get this z term. I'm gonna try to put it in terms of x and y. So how do we do that? Well, you basically just use the relationship that was given to you. Now, again, we're talking about a sphere that is centered at the origin of radius r. If I scroll back up, I already have that relationship right here. Because I have this relationship, I can go ahead and solve for z to put this z in terms of x and y. So once again, I'll scroll up. I'm going to go ahead and take this equation right here, solve for z, and I end up with the relationship z equals to the square root of the quantity r squared minus x squared minus y squared. Now, it should be plus or minus, but keep in mind that this is a physical object we're talking about here. And anytime you have a physical object, you always go with the positive version of the plus or minus, almost always. Now, again, there's that word again, subbing or substitution. It's been all over the place. It's very methodical. It's very consistent. I'm going to take this this expression z equals, and we're going to substitute it into the volume, basically back up into here. It's going to give me this. And also, as we've done before, that's common practice, we're going to want to clean it up. But what's nice about it is that now we have ourselves our function. our function that's going to help us determine what is the maximum volume within the constraint of the sphere. Because notice that the box is being constrained within the sphere. And that word constraint might be familiar to you when we talked about optimization in Calculus 1. Well, that word's going to come up even more so in the next section, 14.8, when we talk about Lagrange multipliers. But the beauty part here is that now that we have our function, look at this little phrase right here, we now resume in a similar fashion to previous examples. Again, it's going to have its own little twists and turns, but the basic protocol, the basic method is going to be the same. So what do we do? Well, what did we do in the previous examples? Once we had our function, we now take the derivative with respect to x, then take the derivative with respect to y, solve them simultaneously by setting them both equal to 0. The same thing happens here. Now here I take the derivative with respect to x, and notice I get a fairly ugly derivative. I mean, that's ugly, right? Because I had to use the product rule, and I had to use I had to do the power rule with a square root, which is no fun. But believe it or not, this is actually, you're able to simplify this fairly easily. And you'll need to do some sort of algebra gymnastics here to get from here to here. But I do highly recommend that everyone in the class get from here to here on your own. And if you're having trouble getting from this ugly expression to this less ugly expression, please let me know, and I can show you the middle steps. I can maybe set up a breakout room or a Zoom meeting where we can actually get together and talk, and I can maybe even write it out step by step. But I feel that most of you could probably figure this out, because you definitely don't want to set this guy equal to 0. It's going to be much easier to set this fraction down here equal to 0, you'll see. Now the nice thing about the symmetry of this function of the volume is that when you take the derivative with respect to y, you end up getting a very similar derivative, except the only difference is instead of y up here, it's going to be an x. Once again, set them both equal to 0. Now, if I set the first one equal to 0 and I cross multiply, it's going to imply either y equals 0 or 2x squared plus y squared equals r squared. And again, I would advise you to go ahead and set this equal to 0 yourself. Cross multiply, and then basically just, it's the second factor here set equal to 0 will give you this. Okay. Also, if you set the other equal to 0, you end up getting this. Now, why am I ignoring the y equals 0, or in this case the x equals 0? Is because, once again, this is a physical object. And typically, you definitely don't get negative values, and typically you don't get values of 0 when you're talking about an actual physical object. So these are my two equations that I end up getting. And what's nice is that they're both equal to r squared. Now again, every problem has its own twists and turns. So you'll have to use your algebra knowledge, your knowledge of geometry, algebra, and all this basic math to do what's right in your eyes and get to the answer. Now, in my opinion, for this particular problem, the easiest way to do it is that, since they're both equal to r squared, is just to simply set them equal to each other, and I end up getting this. Which leads me to x squared equals y squared, which leads us to just simply x equals y. Which is nice because now, once again, I take this relationship and I substitute it back into one of these equations above. You can substitute it into this guy or this guy. It doesn't matter, because you end up taking this equation here. Let's see. You substitute this relationship into this equation, and you end up getting an equation of two variables to an equation of one variable, because r is a constant. And solve for x, you end up getting this. So you end up getting the square root of r squared over 3, which reduces to simply r over square root of 3. And once again, because x equals y, I can just go ahead and set y equal to the same value without having to solve for it again. And much like the last problem, the question was asking you to find the minimum or shortest distance in the last problem. So we had to take those values and plug them in. The same thing happens here. We're not asked to find the values at which this maximum volume occurs. We're asked to find the actual maximum volume. And perhaps in some problems you will be asked for the dimensions as well. But for now, we take this fact that x equals r over rad 3, and the same thing equals to y. You plug both of those into your volume formula, which once again is way up here. You plug in those values of x and y into these values here, the variables, and you should end up with the volume is 8 over 3 rad 3 times r cubed. And I highly recommend that you go through these examples. Now, this is kind of a strange situation where I'm explaining over the internet, and it's hard because it's hard to ask questions. But if you got the gist of what I'm trying to say, for any of these examples, I highly recommend that you go through these examples yourself and try to do them by yourself. And not only do them by yourself, but also, plug them in and actually get to these answers that I got. Don't just assume that I did it right. I could have messed up. I could have made an error somewhere. And if I did, please let me know, because then I can fix it and address it to the class. But, chances are I didn't make a mistake. I did double check these and made sure I did okay on them. And I want to make sure that you understand how to get from point A to point B. So please go through these problems yourself and try them and get to the same conclusions. And if you have any questions, please email me or send me a chat. Now, the final word I want to say about section 14.7 is, once again, this section here is all about finding maximums and minimums. And it's a very methodical, consistent section. I hope you would agree with that. So while each problem has its own twists and turns, you notice that I did a lot of the same methods for every single problem I did. So please take that into account and trust the system, trust the method. And if you trust the method and you do the method properly and use a little bit of your own algebraic intuition, you should be able to get through this section no problem. And this section actually leads very, very nicely into section 14.8, which is, again, Lagrange multipliers, which I'll be discussing next.